We're going to consider another projectile motion problem in which we launch a cannonball or some other projectile at an initial speed v0, but at an angle this time. So we're not going to launch it horizontally off of a table like in the last problem, but at some new angle, and I'll call that angle theta. There are a few questions that we can ask about such a projectile because it follows the same kind of motion, the only difference being the initial conditions here, the speed and the angle. We can ask how far will it go, so this is sometimes called the range. So if you're thinking about a football player punting the football, this is how far down the field the football will go. We can ask, as in B here, how long will it be in the air? And again, with our football analogy, this is the hang time. If the ball is kicked or punted, it spends a certain amount of time in the air before it lands on the ground again. We can also ask how high up in the air will go. That's this maximum height right here, where the ball has left the ground and goes up a certain distance. And lastly, we can ask at what angle will it strike the ground. So the angle that the ball is heading is constantly changing. The angle, of course, is related to the x component of its speed and the y component of its speed. Here, for example, the angle is 0. It's heading straight over to the side. Here, the angle is that angle theta. We can be asking what is that angle throughout the path of this ball. Before we get started on either or any of these questions, it's important to remember that the equations of motion for this ball are the same in the x and the y direction. In other words, x of t is just x naught plus v naught x t plus 1/2 ax t squared, and y of t is y naught plus v naught y t plus 1/2 ay t squared. And likewise, v in the x direction as a function of time is v naught x plus ax t, and vy, the y component of velocity, is v naught y plus ay times time. The only difference here is that the acceleration, which is a vector, is 0 minus g 0. In other words, its x component is 0. Its y component is minus g, and its z component is 0. So we can break our problem down. We don't need quite a three-dimensional system here. We can break it down to a two-dimensional problem. The y direction can be vertical, the height off the ground. The x direction can be the height, or the distance along the ground. And with these kinds of equations of motion, again, it's the same equation in both the x and the y direction. We're just going to have different constants to insert at various lengths away. It's the same equations of motion independently for the x and y component of velocity. It's just different constants we're going to insert for the initial speed and the acceleration.